Welcome to Math 106, Chapter 0.1, where we are going to just start off with just the foundations of some of our math classes. So first off being classifying numbers, then we're going to talk about just different types of number notation, and then we'll talk about a little bit about math sentence structure. And then we go and talk about functions and how to evaluate them. So this chapter 0 is really just a good foundational review of just basic algebra. So natural numbers is really just, it looks like an N with kind of two bars for it when they're notation wise. Kind of is written like this in this form. So what are natural numbers? Can you think about what natural numbers start with? So natural numbers start at 1. Lots of students are kind of between 1 and 0. Natural numbers start at 1. And then what happens? Well, it goes from 1 to 2 to 3, and then it ticks all the way up towards infinity. Now, natural numbers, as you're going to be seeing, are all positive. So natural numbers are all positive, and they start at 1. So then what are whole numbers? Whole numbers, they're a little notation. It's kind of with a W with two bars when you see it. So where do whole numbers start? If you were between 1 and 0, we already used a 1, so whole numbers start at 0. So very much like natural, we just add a 0 onto these numbers. And again, they go all the way up to infinity. Now, are natural numbers found within whole numbers? Yes, so you'll see these natural numbers here that occur within your whole numbers. And if you're looking at your diagram over here, notice that whole numbers aren't shown. However, you could add it here with just encompassing natural within it. Now, integers. Integers looks like a Z with an extra bar. Now, I didn't say this before, but right, what is missing from whole numbers? Because you've added 0 and then went all the way up to infinity, and these are still all positive. So what's missing? So now your negatives are missing, right? So these are both positive and negative numbers, positive and negative whole numbers. So you can go all the way from negative infinity, creep up, and maybe you just do -2, -1, 0, 1, 2, and then go all the way off towards infinity. So you'll still see your natural numbers, and now you're going to see your whole numbers, and they go on, right? And now with your integers, we're adding the negative counterpart. So they all right here are now integers. So all of this. And you'll see that over here in this diagram, right? You have this orange part that is encasing the natural and the whole, the red and the one that we had added. Now, what is missing, right? Well, rational numbers. Rational is Q with a bar inside. Rational can tell us, well, what is missing? Well, we started off with 1, then we added 0, and then we added negatives. So what's next, right? Well, we're missing like your fractional, right? Your decimals. Think about the word ratio. Put it here, ratio, right? So we get to have all of the numbers that are in between. So we can add decimals and fractions. So in this case, we can have negative infinity, and we could go all the way to, I don't know, -2, -1.5. We could have still the -1, right? 0. Maybe we do 1/3, 1, and some of those numbers, right? All the way. Because again, you're still having the natural numbers. You have your whole number here. You have your negative counterparts. And now you're adding, oh, wrong one. Yep, no, actually that was fine. And now you're adding the remaining. Now, when it does come to rational, we do want to be a little picky about what classifies as a specific rational number. So for example, let's take a look at decimals. I'm the worst speller in the world. I'm pretty sure that's how you spell decimals. What is the most common decimal, right? One that we use a lot is 0.5, right? Well, what is 0.5 in terms of a fraction? Well, in terms of a fraction, right, it's just 1/2. Let's do it again. Let's do another decimal. 1.33 repeating. What is that fraction? All right, well, that one would be 1/3. And if we kept going, we could say, okay, well, what's the fraction of 1/5? Well, it's 0.20 or 0.2, right? And you can do this as much and as often as you need, but the common factor when it comes to these decimals or these fractions is that with your decimal counterpart, we want to make it so that your decimals, they fall in one of two categories. Either, number one, they terminate, so they end in a 0. So notice that these ones that we're seeing, they don't end in a 0, but technically after the 5 and after the 2, right, you could add a 0. And it's not just 1 0. You can add as many zeros as you want, and it's not going to change that number. So if it terminates in a 0, that is one of your rational values. Another is that if, maybe I do this in a different color, if there's a pattern or if it repeats. So notice that you have 0.33 repeating. That bar suggests that this number repeats, meaning that I know the next number is going to be a 3. And then the next one after that is going to be a 3. And it's continuous, but in a repetitive motion. Same thing if you were to just have one pattern. You could say this is 3.121212 repeating, ... repeat, right? So it continues with some sort of pattern. This also goes in line with any sort of, actually, I won't say that. Anyway, so that pretty much takes care of rational. You'll notice that rational numbers here, right, encompass your integers, your whole, and your natural. So then what is the opposite of rational? Well, you have irrational. And this is, again, typically Q with a star. Now, irrational means the opposite of rational, meaning the opposite of rational. Well, if rational is this yellow part, that means it's not natural, it's not whole, it's not integer, and it's not rational. So that means that none of these rules apply. So it's not numbers like 1, 2, 3, or 0, or -1, -2, -3, or decimals that terminate or repeat, or its fractional counterpart. So it's none of that. So that means what is left over, right? Well, if we're talking about some unusual numbers, what is the most famous irrational number? Well, that would be numbers like pi. What is pi? Well, it's 3.14 ... The ... suggests that this is continuous without pattern or repeat. Some of us know what comes after the 1 and the 4, right? But after a while, no matter if you've memorized the first 2, the first 10, the first 20 numbers that come after in your decimal, you have to stop because this is infinite. It keeps going without repeating, which means it is irrational. Another famous one, I wouldn't say famous, well, another one, E is pretty famous. E is 2.71 dot, dot, dot. Again, the dot, dot, dot is continuous. And we'll talk all about E in chapter 4 and 5. So if you don't know what E is, that's okay. But again, it's going to be continuous without pattern. Now, there is another one that we haven't quite talked about. This would be, let's say, the square root of 2. What is the square root of 2? Well, we could kind of estimate what it is. It has to be a number that's in between the square root of 1, which is what? Well, the square root of 1 is 1. And the square root of the next number that comes out nice and clean, which is the square root of 4, which is 2, right? So the square root of 2 must lie in between the number 1 and 2. It happens to be 1.41 dot, 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 repeating again without pattern or repeats. So that just means any sort of square root that comes out unclean, so not like numbers 1, 4, 16, 36, and so forth, right? That would be considered irrational. And you'll see that over here, where it has that irrational I. It's not really I, it's a Q star. Imaginary is the one where it's really I with 2 bars. Luckily for us, we won't have to get into imaginary or complex. We don't have to work with these. We're just going to keep within this green bubble. So now the last one being real numbers. If you've heard the expression all real numbers, they're just saying, hey, take all of these numbers that we've just talked about. 1, 2, 3, 0, 1, 2, 3, negative infinity, -2, -1, 0, 1, 2, 3, and then all of the numbers that fall in between. So we are really talking about the numbers that are between negative infinity to positive infinity. Now, the reason why we talk about these classifying numbers is that on your homework in blue, and if you don't, well, I guess we are using Pearson, so ours are going to be in blue. There'll be a little font that says how to structure your answer. So you need to be aware of, okay, well, what is an integer, or what is a reduced fraction, or so forth. Okay, so you need to understand what classifying numbers is in order to complete some of your finer homework problems. Now we're going to move on to interval, inequality, and graph notation. So for your interval notation, interval, we either have parentheses or brackets or mixed. Now, when we want to exclude a number, so get as close to it as possible, we're going to be using a set of parentheses. To exclude means that we are not including that number. We do not start on that number, but we can come close to the number. Come close to the number. When we want to include that number, we're going to be using a bracket, meaning that we can start on, or start / end on that particular value. And then, of course, you could have a mix of it where we can use parentheses and brackets together. So for an example, if I'm using these parentheses, we could say parentheses 1 to 4. So in interval notation, we're going to get as close to the number 1 as possible. So that could mean 1.00001, right? Not quite 1, right? It's a little bit more than 1, but we're going to get as close as we can. And that's just an example. We could put many more zeros and then a 1, right? As close as we can get to 1 as possible is when we're going to start. Or its opposite counterpart, as close as we can to 4, 3.9999999, practically 4, right? We're just not going to include 1 and 4. Same thing over here, except we're using brackets around the 1 and the 4, meaning that we get to start on 1. We get to end on 4. Now, we always read left to right, just like we do on a number line, just like we do when we're reading a book, left to right. That means we're going to start on 1 and end on 4 versus start close to, and I think I use the example 1.0001, and this time we're going to end close to 4. And then of course you could have some sort of mix. Don't start on 1, but end on 4, and all of those numbers in between. Start on 1, but don't end on 4. Get as close as you can. Now that is just for interval notation, so parentheses and brackets. Inequality is the one where we talk about greater than and less than. So we could say greater than or less than. Greater and less. Now, if you have a hard time remembering which one is which, just think when you spell the word greater, it kind of looks like the R of the greater in here. Or for your less than, it looks kind of like an L for your less than. And I know there's something like the alligator or the shark or whatever, or I can't remember some of those analogies from way back when, right? But think about greater than and less than in terms of just written words, I would say. Now, because it's just greater than or less, again, we're going to come as close as we can to those specific numbers. And again, reading from left to right, this time when we use your notation, we're going to need a variable. Now, typically we talk about domain first. We're going to talk about why that is here in a moment or in a little bit. But we could say 1 is less than x, or x is greater than 1, depending on which direction that you're reading it in, which is less than 4. So again, this is just saying start as close to 1 as possible and end as close to 4 as possible. Now, when we want to include those numbers, we're still going to use the same symbols. We're just going to add this little bar. Now, that bar looks like the equal sign, just we've cut off part of it, right? Normally, equal sign is 2 bars. We've taken it away, right? So that's greater than, and then we have less than or equal to. So this is greater than, or, and I'm going to highlight maybe this in orange. So this is greater than or equal to, or this is less than, or again, equal to. So again, this is just saying, hey, we are equal to that value, whether you start or stop on it. So again, you could say 1 is less than or equal to x, which is less than or equal to 4. And then of course you could have any sort of mix. You could have a number less than or equal to x, which is less than or equal to a number. Or I was supposed to mix it up and I didn't. I don't know why I'm just doing numbers. Why don't I just keep with my 1 and my 4? And do it this way. Now you'll notice that these are written. Oops, I did not do that correctly. I was going to say these are written in the exact same notation. However, now they are. So these are written in the exact same manner, just using a different notation. So you'll notice that you have the bracket or the equal to bar, the bracket or the equal to bar. This is interval. This is inequality. Now our last one is graph notation. Graph notation, if we want to exclude a number so we come as close as we can to that number, we're going to use an open circle. So open circle kind of on this number line. So for us, if we wanted to signify that we want to get as close to 1 as possible and then go all the way to the number 4 and get as close to the number 4 as possible, meaning that on this little number line, we have the number 1 and we have the number 4, meaning that we're going to open the circles on these values. And when it comes to this region, we're going to highlight or shade between these two bars, meaning that in pink, right? Let's say we have 2, we have 3, maybe this is 1.5, maybe this is 2.5, maybe this is 3.11, right? But we're talking about all of the numbers that we can be. And maybe over here, we get to 3.9, and then 3.999 would be next to that. And we're going to get as close as we can to 4 without stopping directly on 4. And then similarly over here, if we wanted to include the interval between 1 and 4, instead of an open circle, we're going to be using this closed circle. So for us, if we're doing the same sort of example, 1 and 4, instead of an open circle, we're now going to close it. We're going to close the circle. And we can't just leave it like that. We need to highlight some interval. If I highlight the in-between numbers, just like we did over here, that's just telling myself, okay, I want the numbers that are over here, in between 1 and 4, versus if I highlighted over here and not in between, that would be the opposite, from negative infinity all the way to 1, and then skip this part, and then from 4 all the way up to infinity. But for us, we're just interested in the numbers starting at 1, all of those that are in between, and then go all the way up to 4. And then we can stop after that. And again, we get to include 1, we get to include 4, right? Start and stop, or start and end on those values. Then, of course, you could have some sort of a mix. You could have open on one end, closed on another, or closed on one end and open on another. So for us, you could say on this number line, 1 and 4, and again, 1 and 4. You could open 1, close on 4, highlight in between. I can start as close as I can to 1, go all the way and stop on 4. Or I can start on 1 and go all the way to 4 and get as close as possible to 4. And again, these are all the same exact notation. The same exact, they're saying the same exact thing, just in a different notation. Now we're going to get some practice with writing these as well from example 1. And there is a worksheet that I think we'll cover in our next video here on just some of these notations. So let's see what you picked up from that little portion and try out example 1. So it says x is greater than 4. Keep in mind, when we go from writing sentences, and it also says write in 3 notations, start whichever you're comfortable with. When it says x is greater than 4, well, I now know the greater than symbol is really the one that looks like this one. So we have x is greater than 4. Now, some other homework that you might see is that sometimes they like set builder notation, which it's an additional notation. It's really just your interval, but just taken a little bit further. They can just say that this is like a little brace, and it says that of all your x's, such that x is greater than 4. They're just defining, okay, we're going to take all x's that we're going to see from here on out, and they will be defined as being greater than 4. So that is your inequality notation. I might put it in my graph notation next. So if we're just saying that number 4 is up for contention. Now notice that it said greater than 4. It didn't say greater than and equal to 4 or equal to 4. right? Therefore, I'm not going to include 4, meaning that it's going to be an open circle. We can get as close as possible to 4. Then when it says greater than 4, well, what numbers are greater than 4? Well, that would be 5, that would be 6, that would be 7. But it looks like we're going to go off towards positive infinity, towards the left. So when I go to shade or highlight, I'm going to be shading towards the right-hand side. I may have said left a second ago. Don't know why I get my lefts and rights confused. We're going towards the right-hand side, towards that positive infinity. Now, what is nice about your graph notation is that you could also write it in a different form. If you didn't like how you use a circle, you can also use a parentheses as well to signify it's kind of getting us set up for the interval notation. Now, parentheses is for open circles, meaning that if it's a closed circles, we can use a bracket. So it's either condition that you'd like. Some of us can do both of them. I like using both. It's just me. Now, when it comes to your inequality, your interval, we're going to start with your parentheses at 4. And then we're going to go all the way up until we get to the pos infinity. We always read left to right, left, and I might do it up here. Left to right on your number line. And therefore, when we write it, it's always your smallest number first to your largest number. Now, what's nice is that your infinity sign will always have parentheses. Whether that's positive or negative, will always have parentheses. Now let's do it again. X is less than or equal to -6. So again, pause the video when you're comfortable. When we know that less than or equal to, hopefully, is this little symbol here. So we can say, okay, X is less than or equal to -6. Or if you're using set builder, we're doing braces X such that X is less than or equal to -6. Again, this is set builder. And then again, maybe I do my graph notation. We have -6 up for contention. It is a equal to counterpart. So this part having the equal to word, meaning that we are now using a closed circle. Or instead of a closed circle, if you want to use a bracket, I would say wait to use a bracket until you know which direction you're shading. If we're saying it's less than or equal to -6, we can be -6 or anything less. Less than -6 is -7, -8. And we're going to go off towards the left-hand side towards negative infinity, meaning that we're going to be shading in this area. Again, the shading is necessary. Your bracket, if you want, will go towards that side. And again, we're going to read from left to right or small to large. So when we do your interval notation, what is on the left-hand side? What is the smallest number that you see on this number line? Well, we're going to go all the way from negative infinity, which we said will always have a parentheses because it's not achievable. You cannot be equal to negative infinity. It's kind of like one of those dreams where you're running towards the end of the hallway and you just can't get to the end. Okay, you cannot achieve infinity. Right, and then we're going to go all the way towards the right and we stop on 6. We get to include 6. Now let's just do example 2. It says convert to inequality and graph notation. So you'll notice that this is in interval notation. So for your interval, notice that it is 2 brackets, meaning that we are equals to, equal to. So what is nice is that we can actually write both of our numbers and we'll use the value X, thinking that these are maybe numbers defined by your domain. And what's nice is that when it's in this notation, we can just put these two symbols, because when we read it, we're just saying, okay, -3/4 is less than or equal to the values that are going towards 5. So -3/4 is less than or equal to x, which is less than or equal to 5, meaning that x can be any number between these two values. Close circle here because we're equal to, and then shading in between. We can be any number. We could be 0, we could be 1, we could be -half, right? We could be any number under in between. Now let's do it one more time. When it says x is greater than or equal to 10 in interval and graph. So if you wanted to graph it first, 10 is up for debate. We have the equals to sign, which means we are working with a closed circle. Or if you wanted, you can use brackets. I didn't use the bracket before. If there was no bracket, if there was no equals to sign, we could use parentheses. So x is greater than or equal to 10, meaning that all numbers that are bigger than 10, so that means 11, 12, 13, so we're going to go off towards pos infinity to the right, should be shaded. Again, I need that pink line to show us where we're going. Now, when it comes to your interval, right, we're going to say, well, we're starting on 10. We're going to go all the way towards infinity. Again, do not include infinity for your graph, your notation. Now let's talk about translating sentences into equations. So this should say example 3. Oh, well. So what we're going to work on is just picking out what we know. So if this is something that's hard, just figure out, okay, well, what do we have, right? Well, it says 4 more than a number. Well, 4, that translates easy, just the number 4. More than means, are we adding to it or taking away, subtracting? Well, more than means that we're going to add something to it. And then when it says a number, this is just talking about a variable. Pick a variable. Typically, I go with x. And when we go to write it, right, this is one way to write it, 4 plus x, or x plus 4. When it comes to rules of addition, either way is perfectly fine. But when it comes to subtraction, we have to be cautious about what value is being taken away, what's doing the action, what's doing the subtraction. So if we look at your next one, 2 less than half of a number. Well, when it says 2 less, right? Well, we know the number 2. Less than signifies subtraction, which I'm going to put like a parentheses around it. Half of a number. Well, what's half of a number? We said that a number stands for a variable. We'll just say that that's x, and we're going to take half of it. And you might not know what of means, but of is multiplication. Now, what is doing the subtracting? Well, the action of the word suggests 2 less. 2 less. That means we're going to take away 2 of half this number. So 2 is doing the subtracting. Doing the action. Subtracting. So one way to write it is saying, okay, well, we're going to take half of this number and we'll subtract by 2, right? You could also write it, actually a couple different ways. You could also do it as such when multiplying, right? This x, what we're going to learn, has a coefficient, a number in front of it. your coefficient right now is 1/2, but let's say we wanted to separate it for now. When you multiply it in, you're multiplying your top to top and bottom to bottom, right? The ghost one there. So it can turn into division when you have a fraction. So that's also a good way to put it. You could, if you wanted to, write it a third way. You could also say -2. You're taking away 2 from half the number. So you can write in any of those 3 notations. What you can't do is say, okay, this is 2 minus 1/2 of x. That is suggesting that you're taking half the number away. You are taking 2 out of that number. So try it again. It says the difference between 3 times a number and 1. Now, when it says it like this, the difference between, the action is coming first, which means that we can go in order. So if the action comes first, then we can go in order. So the difference signifies subtraction. So we'll be subtracting in order. It says 3 times a number. 3 times, so multiply a number, we'll say x, and 1. So going in order means that we will then be subtracting the 1. So again, one way to write it, 3x minus 1, or -1 plus 3x. Notice that the 3x is positive in this case. It's the one that is doing the subtraction. The difference between 3 times a number and the 1 doing the subtraction. So it says, if the action comes first, then write it as you read it. So go in order. All right, if you haven't paused the video, try it now. It says 8 more than the quotient of 1 and a number. So 8 more. So again, that's an action word. So 8 is doing the action. So we have 8. When it says more than, and I should highlight this word too, more than. So 8 is doing the adding, right? So 8 is positive. The quotient of 1 and a number. Well, we talked about a number, that is our variable. And it says quotient. Quotient is division of 1 and a number. So divide 1 and x. So if we put it all together, we can say 8 plus 1 and x. Or because it's rules of addition, we could write it as such. This is the quotient or the division between 1 and a number. If it said 4 in a number, or 6 in a number, or -5 in a number, right? That beginning part should be up in your numerator. Now let's talk about evaluating functions. So it says a function is when each independent variable, an independent variable for us is x, has its own dependent variable y. Lots of textbooks, I think ours, this is your yours from your textbooks when it talks about a function, right? A function is when each independent variable x has its own dependent variable y. Not the worst sentence in the world. They do get wordy when defining what a function is. What they're talking about is that x's do not repeat. Okay, do not repeat your x. Okay, so to think about it, if those who are in the dating pool, if you have an ex, you might not want to consider dating them, right? So don't date the ex again. Therefore, as long as they do not repeat, it is a function. They're also just saying 1x per y. So for example, we have ordered pairs below. Determine which are functions. So based on the little sentence, x's do not repeat, which ones are functions? Pause the video, see what you can do. We have your first one. Is it a function or not? Yes, it's a function. You have the number 1, 3, 5, 7 does not repeat. Let's do it again. Your next one. You have 2, 4, 1, 2. Which number repeated? The 2 repeats. Therefore, x repeated, it is not a function. How about the last one? We have 2, 4, 7, 5. Did your x repeat? No, right? Your x didn't repeat. Your y repeated though, but did we say anything about having an issue with y's repeating? No, it's just your x value cannot repeat. So this is, yes, it's a function. It's okay if y repeats. Now, all these ordered pairs are just found on your graph. So plotting the point, the coordinate, right? For your coordinate, this is an x value, and this is a y value, an x, a y, an x, a y, an x, a y. So what we're going to be doing is starting to evaluate these functions. We'll end up graphing these functions. Now, if this is an idea just given to us as a coordinate, let's try it again here, right? So it says if x values do not repeat and x is equal to a is just signifying it's going to be a value, a number, is a vertical line. Determine which graphs are functions. So if we know that your x values cannot repeat, a quick test is to do a vertical line test. If I draw a vertical line through these 2 graphs in blue, which one would you say is the function and which one is not? Well, if I look over here, my first one only touches once and my second one touches twice, meaning that if I were to put these in coordinates, let's just say a random coordinate, maybe this is a 2 and this is a 1. And maybe this is a 2, a 0, and maybe this is a 5. Well, I can make the coordinate 2, 0 and 2, 5. Which one is the function? This one is the function and this one is not. Therefore, if we were to come up with an idea, right? Generalization. When graphs are given, we can use our vertical line test. If the graph touches the vertical line once, we can assume what? It's a function. If the graph touches the vertical line more than once, as long as it hits again, we have this situation where it's now repeated. So it is not a function. So if graphically we want to determine if it's a function or not, all we have to do is draw a vertical line to see if it'll pass. Now, do you think if there's a vertical line test, is there going to be a horizontal line test? Yes, there will be a horizontal line test further on. This is just to test if they have a natural inverse, a natural opposite counterpart. So now let's do away with graphs and see evaluating functions. We can find points when we evaluate. So if we have, and I'll put that on here, points, right? Notice how we started off with points here. You're graphing it. All you have to do is find the point. Now, if we're just given a function, if we know part of it, if we know what your x is, we can therefore find your y. And they're just saying, okay, well, this x is now equal to 2. All we have to do is substitute it in. Y is equal to, parentheses, 2 squared Therefore, 2 squared is 4. So we have the coordinate. My x value is 2, and whatever came out is my y coordinate. So this is a point on our graph. Now, if you didn't know what this graph looked like, this is actually a parabola. It is a quadratic. Oh, not the best. Here we go. So it's just saying this is my coordinate here at 2, 4. Now, does this pass the horizontal line test? Well, at any point, we can draw a vertical line and it will end up passing. So this is a function. And the reason why we want it to pass and figure out as a function is that we want to make sure that the one x value that we pick only maps to one y value. So we have, by definition, we know the exact solution, the exact counterpart. So in order to successfully evaluate, all we have to do is replace the variable x with the value. So that is all we did here, was replace your x with that value. And all you come up with is the particular point 4, 2, or 2, 4. Now let's see if you guys can try it again in example 3. So this time we are evaluating when x is -2. So we're going to replace all of the x values that you see with the 2. Order of operations still apply. So we can say, okay, 3, and we have our 2 here, which is squared, plus 2 times our 2 here, minus 5. So orders of operation says we must square 2, or sorry, this is a -2. And then we can multiply, right? Please excuse my dear Aunt Sally. All right, so let's see, -2 squared. If it's been a minute, -2 squared is just saying this is -2 times -2 twice. So we are multiplying these two numbers together, meaning that the negatives are going to cancel. So it's a positive. 2 times 2, 4. Then you have a -4, so 2 times -2, minus 5. So you got 12 minus 9, which is equal to 3. So you have the coordinate, you put in a -2, and you got out a 3. This is a coordinate. Let's see if you can try it again. So pause video, try it out. So y is equal to the square root of 4 and 1/2 plus 1. So this is, if you wanted, we're multiplying 4 times 1/2. 4, your denominator can just be a 1, so you can multiply straight across if you'd like. 4 divided by 2. So the square root of 2 plus 1. Now, believe it or not, this is a coordinate. So you could estimate it. This is about 1.41 plus 1. So you're about 2.41. But if you wanted an exact coordinate, this could be the y coordinate in itself. Now, to try this exercise one more time, let's try it again, but this time when x is equal to 4. Or sorry, 1/4. Okay, so if we're doing it again, because I don't think I picked a very good number, 4 times 1/4 plus 1. Well, we have 4 times 1/4, so that is just 1, because 4 over 1 times 1 over 4, multiply top to top, bottom to bottom, 4 over 4. It's just another way to say 1. Plus 1, the square root of 1 is itself 1. Therefore, y came out to 2. So we have the coordinate 1/4 and 2, or you could say this is 1/2 and 2.41 approximate. You don't really need those. Okay. So let's try example 4. And I believe this is our last. No, we got one more page. Sorry, this is a foundational, a lot of this one. This says, example 4, evaluate the function given a graph, write your answer again as a coordinate. So instead of given an equation, we are given a graph and we're expected to evaluate. So when x is equal to 5, what is its y counterpart? Well, when x is equal to 5 on your graph, that would be right here. What is y? Well, y is 0. So as a coordinate, 5, 0. Be careful on my test. Don't just put 0 in the directions. It says write it as a coordinate. Give me the coordinate. Try it again with b. When x is 3. So this one you're going to have to do a little bit of estimating. So if we know that over here at 2, we have the y coordinate of 3, we should be anywhere less than 3. I don't know if we're quite at 2. 2 would probably be about here. So give it a rough estimate. We could say this is 3 and 3 over 2, or 2.5. Up to you if you like fractions or decimals. Let's do it one more time. C is negative 1, 3 on your graph. Well, when x is equal to negative 1, what is your y coordinate? Well, your y coordinate is 0. So does that mean negative 1, 3 is this coordinate on your graph? No, not on the graph. Now, let's talk about domains of functions. So it says domain is always the horizontal x value. And their graphs. So it says we read it from left to right, smallest to largest. Range is always the vertical for your y values. And we write these from bottom to top, again, smallest to largest. So when it comes to lines, quadratics, square roots, and rationals, we're going to be taking a look at your domain and your range. So when we look at your domain here of this line, right, from left to right, on your number line for your x values, we have negative infinity and infinity, right? So and notice that this green line is nice and solid. There's no holes and gaps. There's no jumps that we have to account for, but it's nice, solid, smooth line. So your smallest x value, if we were to keep going, let's see, it doesn't stop at negative 3. It keeps going to negative 4, negative 5, negative 6, because these are going to just keep going. We can assume that it's just going to go off the page, meaning that your smallest x value happens to be negative infinity. We go all the way towards, again, the right-hand side, past 4, past 5, past 6. It's just off the page. Now, when it comes to your range, we are reading from bottom to top. Again, with your y values, we're going to read from bottom to top. So what is your smallest y value? Well, again, it goes off the page. So we are assuming we go from your smallest negative all the way to your largest. So one more time, from negative infinity to positive infinity. Let's do it again with your quadratic. From left to right, assuming that these are going off the page, there's no gaps, there's no holes, there's no jumps that we have to worry about. It's nice, solid, smooth line going from the left-hand side where your x values, each x value that starts, we have negative 1, negative 2, negative 3. It's going to continue off your page, negative 4, negative 5, all the way from negative infinity. So you're starting super small at negative infinity. We go all the way off their page to your right. Now, when it comes to your range, what is the smallest Y value that you see. Again, we're going from bottom to top. So while we may have negative infinity down here, is any of your graph down here in the negative? No. The first Y value that you encounter is here at 0, 0. So we're starting at 0. And notice that I'm using now a bracket because even if I erase this point, it's nice, solid. There's no open hole. It's a nice continuous green graph. So we're starting at that point, meaning that we start at 0. Now, where does your graph go? Well, your graph is going up towards infinity. So we can go all the way towards infinity, which we do not include. Let's try it again. Again, assume that this one is continuous, goes off the page. Now, what is happening here? Does it look like our graph continues? No, it stops, but where did it stop? What coordinate? Well, it looks like it stopped at 0, 0. And again, it's not showing an open hole. It's nice and green, and it just stops at that coordinate. So what is your domain by looking at it? Well, your leftmost point, well, yeah, your numbers can go all the way to negative infinity, but notice that the green graph isn't anywhere over here. Instead, the first portion of your green is at your coordinate, 0. And better yet, we are starting at 0. There wasn't an open hole. It's at 0. And then where does your graph go? Well, then at 1, we have part of your graph, at 2, 3, 4, and it's going to go off your page towards infinity. Let's do the same thing for your range. Again, your range, your numbers do start at negative infinity, but is there any part of your green graph showing there? No, there's no green graph down here until that coordinate again. And where does your graph continue? Well, at 1, we're all the way at 1. At 2, we're not quite there. We're at about 1.4, right? At 4, we're all the way up at 2. And again, this is going to get bigger and bigger, meaning that we're going to go all the way towards infinity. All right, domain and range. See if you can pause video if you haven't done so already. Now, we haven't covered this quite yet, but these are called asymptotes when your graph behaves in such a way. It's just saying that your graph is not going to touch these axes. These are called asymptotes. So where do these asymptotes occur? Well, this one occurs when y is equal to 0. And this one occurs when x is equal to 0. And yes, I know horizontal looks typically an x value, but this is where all of your y values are going to be 0. At 1, 0. At 2, 0. At 3, 0. So you'll notice that your y value isn't changing, but your x value is. And same idea here, just with your x. So your x values, they start all the way at negative infinity, right? The green graph continues off the page. So we start all the way at negative infinity, and then we go all the way, and now it rockets down, but downwards is your y value. What's happening as far as your x values go? We have a graph at -3, at -2, at -1, at -0.5, at -1/3. Where's your x value going? Your x value is going towards this x, but we just said an asymptote, we can't touch it. So we're going to go all the way to 0, and we're going to skip 0. We can't touch 0, so we're going to skip it. And then to say on the other side of your graph, this is called a union. We're going to start at 0 because, again, we can't touch 0, but then at -4th, -1/3, -0.5, then 1, then 2, then 3, we do see your graph. We're going to go all the way to infinity. Try it again with your range. Your range is going to look the exact same, but just from your y perspective. So again, from bottom to top, so from the lowest part of this green graph, it's starting all the way down at this negative infinity. And then as we see it up here, we have a -3, we have a point at -2, at -1, at a -1/2, a -1/3. And it's going to try and approach when y is 0, but it's going to have to jump. And when your graph jumps, notice that your x value on the other side, your x value is at 0, right? We're still not touching. And then at your y value at a third, a half, we're starting to get there. At 1, we're at 1. At 1.5, we're over here on your graph, and we're going to continue to grow up. All right, now for example 5, see if you can write your domain and range of your functions in interval notations compared to the parent graph. So these are your parent graphs that we've just kind of defined. See if you can do it again with your line, with your root, and with your quadratic. So we got a nice solid line. So if we're ready for it, your domain and range are both all real numbers. So they're going to go from -infinity to +infinity. Same thing with your range. Very much like this line here. There's no holes to account for. There's no gaps. There's no asymptote. No funny business. Nice solid line throughout. So this matches your line exactly, meaning that any line going from here on out with no holes or anything should all be all reals. Let's look at this root function. All right, so it looks like your x values, we're going to start at this coordinate. The coordinate is 2, 1. Your x values are going to start at that 2. So your domain here is starting at the 2. And it looks like that each x value that we see, we're going to continue off towards infinity. And your y value, your range, we're going to now start at the 1, the smallest y value, because there's no y values that are smaller. And then we're going to continue to grow all the way again to +infinity. Similar to this graph. Oh, and hopefully you caught that mistake. My mistake, I used parentheses. I think I was looking at this parentheses. We need brackets because we are at that point. Notice that there's a solid dot at the coordinate 2, 1, meaning that I have to include. So when you look at your root over here, all we've done is we've shifted this point here to go over 2 and then up 1, and then you have the same sort of graph. One more time here. Same idea as before. Your domain is all reals, -infinity to infinity. And your range here, your smallest y value happens to be at this minimum of -2, -3. We're taking your y value. We don't need your x value, -2, because that's already found within here, your interval. Instead, we need your -3. And we'll start at -3 because it's a nice solid dot here. And we're going to grow all the way up to infinity. So we're going to go all the way up. So if we look at it over here, like your quadratic, domain stayed the same. It's your range that's going to change. All you're doing is you're taking this point and you're going to move it. I think we moved it over, what did we say, over 3? Nope, over 2 and down 3. So we took this graph, we moved it over 2 and down 3. So that just changes your range here, but keeps your domain the same. And that should wrap up your functions, your intervals, all that jazz.